the universe must have been hotter in the past and smaller. And we can actually see that when we look at wavelengths of light. Right now, the light that we see out in empty space is very, very redshifted. So in the past, because the universe is expanding, it must have been the opposite. It must have been more and more blue shifted or higher and higher energy. So we can use our current light that we can see now to see, hey, it must have been hotter in the past. And that heat must have come from somewhere, probably radiation left over from the Big Bang, right? Now let's go ahead and take a look at what is the temperature of space right now. Well, right now it's 3 Kelvin, but what if we were to go back in time? So let's look at light from different places back in time. So right now, 3 Kelvin. If we look at a galaxy that's about 7 billion light years away from us, so, it's about 7.2 billion years old, about average. If we look at that galaxy is only about 6 Kelvin. So it's double the temperature that it is right now. So half the universe ago, we only doubled the temperature. Well, let's get even older. Let's look at a galaxy that's about 12 to 13 billion years old. So it was formed only about a billion years after the Big Bang. We look at the space between that galaxy, and it's about 73 Kelvin. So for comparison, way colder than anything here on Earth still, but, not 3 Kelvin. Okay, well, let's get even hotter than that. So as you can see, as you get farther and farther in the past, now to about 6 to 7 billion years ago, to about 12 to 13 billion years ago, and the temperature gets hotter and hotter and hotter. So what's happening is, as you go more in the future, the wavelengths are getting stretched out. If you go into the past, they must be pushed back together. And as you know, closer wavelengths, shorter wavelengths means higher energy. Longer wavelengths means lower energy. So it must have been shorter wavelength, higher energy light in the past. So let's find out. So we go to only a few 100,000 years after the Big Bang. And the entire universe, if we were to extrapolate it back, would be about 10,000 Kelvin everywhere. And at this point, it's cool enough, I should say hot enough, but it's really cool enough for actually atoms to form. So hydrogen and helium were actually formed at this time. Before that, they were all there. The electrons, protons, and neutrons were there. It's just they didn't want to stick to each other. It was just too hot. Everything was a plasma. But once you reach about 10,000 Kelvin, atoms can start forming. So you can get, protons, neutrons, electrons, they start coming together. You can get hydrogen, helium, a little bit of lithium as well. Let's get even farther back in time. So about 3 minutes after, and the universe should be about 1 billion Kelvin. And that's like the temperature of inside of a really, 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 really hot star. So at this point, you're definitely only having plasma. The main takeaway from this is, as time passes, space cools down because our universe is expanding outwards. And we can see that when we look at distant galaxies that are hotter than our own current galaxies nearby us. Testing. If the universe was denser and hotter in the past, shouldn't we see some evidence? How do we know that it was hotter in the past? Other than looking at distant galaxies, what evidence do we have? So what do you think? What's one thing that gives temperature of space? Light, radiation. Yeah, that radiation is everywhere, and that radiation came from, well, the leftover stuff from the Big Bang. Even the stars themselves come from energy from the Big Bang. So yes, where is that heat now? All around us. In fact, this is the cosmic microwave background radiation in a picture form right here. And I would recommend writing this down, the cosmic microwave background, or CMBR. You might see either. You might see the abbreviation, you might see it written as words, but they both mean the leftover heat from when atoms first formed. So the CMBR, what is the cosmic microwave background radiation? It is the leftover heat from when atoms first formed. It is the heat from the Big Bang. Basically, the light that left after atoms formed, because once atoms formed, all the light is blocked. That light is still there today. And using satellites, specifically the COBE satellite, as you'll see later, we can actually see that now. Now, you don't have to have a satellite to see some of these microwaves. In a second here, I'll tell you how you can actually see the CMBR at home. If you have an old style TV, one with an analog tuner, if you change it to a channel that doesn't exist, so just pick any old channel that there's no broadcast on, you'll actually see some of the static. That static, some of it is leftover CMBR, some of that microwave radiation that's still out there in space today. It's here on Earth, it's in your room, it's everywhere. And it gives temperature to everything in the universe. Now, it doesn't give much temperature, right? 3 Kelvin. Microwaves really aren't that strong, but it does give some temperature to everything. Now, why is it microwave? The light from the cosmic microwave background didn't start out a microwave. It actually started out as visible light, yellow, reddish. But what happened is over time, as the universe is expanding, that yellow-red light has been stretched out and lost energy. And that lost energy means it's moved from light to infrared back to microwaves. And actually, we can see that right here. Distant galaxies, we can see those with infrared light. Yes, they're redshifted, but they're still redshifted only a little bit from, visible light into infrared. But if you want to look all the way back here at the cosmic microwave background, the universe has been expanding the whole time, and it's been stretched out way more than galaxies. So in some point far into the future, even the cosmic microwave background won't be the cosmic microwave background anymore. It'll be redshifted enough to be the cosmic radio wave background. And then, even these galaxies right here, they'll move from infrared to microwave to radio waves. And then there's nothing beyond that point. It just keeps getting stretched farther and farther and farther and loses energy and loses more energy. So since energy can't be created or destroyed, as the universe gets bigger, all the energy in it just gets more and more spread out. It doesn't get, there isn't more heat being made, even though you might think stars are basically nothing compared to the size of the universe. So all the energy that was left over from this is still there, but it's just more diluted everywhere, if that kind of makes sense. Now, here's a picture format to express that. And if we look, there's the cosmic microwave background, formed pretty recently after the Big Bang. And then there's the dark ages, where there weren't any stars yet. They hadn't had time to form. Here's where stars and galaxies started to form. And basically for the last 13 billion years or so, it's just been stars and galaxies, stars and galaxies, stars and galaxies. But you'll notice something. There were a lot more stars and galaxies clumped closer together here. And if you look right here, you were here in time, there's a lot less. So what's happening? Well, look at this curve of this diagram. After we go farther towards the present, you'll notice that the diagram gets bigger and bigger. It curves outward. The universe is expanding, and since it's curving outwards, it's expanding faster and faster as time goes on. So all these galaxies are going to get more and more diluted. All the cosmic microwave background radiation is going to get more stretched out, and it's happening even faster than it was in the past. And there's another problem. There's two parts of the universe that are missing. First of all, what's holding those galaxies together, right? Because if we look at galaxies and stars, they're moving faster than they should be, especially even our own Milky Way galaxy. Some of the outer edge of the stars, they shouldn't be sticking around with the galaxy. They should be flying off into empty space, intergalactic space. So what's holding galaxies together? Dark matter, I should say. And here's the thing. We don't really think it's missing. We just think that we can't see it. It's something that we can't see. It could be WIMPs, weakly interacting massive particles. It could be mini black holes. We don't know. There's like 31 experiments that have been ran to try and figure out what dark matter is, and there's some current experiments running right now. So this might be something in a couple of years, maybe a couple of decades, they'll actually figure out. Keep in mind, at some point in the past, they didn't even know that there was water on Mars. So keep an eye out. We'll probably figure out what dark matter actually is at some point. So we just can't see it. It may be invisible, maybe it's not. The thing is, we just don't have enough light to actually see it. It doesn't interact with light, or it's just not bright enough. Now, as far as what's causing this expansion right here, well, that's not dark matter. Dark matter would want to hold the universe together. So all you need to know is what's causing the expansion is dark energy. Nothing to write down here. We don't know what dark energy is. We just know it's something that's making the universe expand. And to make the universe expand and to accelerate it, it takes energy. And that energy is coming from something we don't know what it is. So while dark matter is probably something we can test, we have no clue how to test for dark energy yet. There's a couple leading theories. I'm not going to put them in here because you don't need to know them. There's plenty of videos on YouTube about that. Let's go ahead and move on. Just know dark energy making the universe expand, whatever it is. Yeah,